In this video, we're going to talk about circle theorems, and we're going to look at a lot of examples under circle theorems. Before we start, I would like to show you how the course is structured. First of all, we'll talk about parts of a circle, and then next up, we talk about each of the theorems. After talking about each of the theorems, I'll look at some examples on those theorems. So when we are done with all the theories, we will now look at questions that needs us to apply 1 or 2 or 3 or 4 of those theorems. So that's how the course will be structured. Now you can check the description of this video to skip forward to the calculation parts or the example parts, or to skip backwards. So with that said, let's get into the video and talk about parts of a circle before we get into the theorems. So for the first section of this video, let's get into the parts of a circle. We already have the parts listed out here. I will just show you how they look like in a circle. Say we have a circle like this. The first on our list here is the center of the circle. So the center of the circle is simply the midpoint of the circle. There's an equal distance from this point to this point, this point to this point, this point to this point. So we call here the center of the circle. And then for the second one, the circumference of the circle. The circumference is simply the outer part of the circle. So this part of the circle is called the circumference. So I'll write here as circumference. For the next on our list, we have radius. The radius is simply a straight line from the center of the circle to the circumference of the circle. Any line. So if I have this line to circumference of the circle, this is a radius. This is also a radius. And then for us to continue, I would like to draw another circle. So say I have another circle here. For the next on our list, the chord. So a chord on a circle is a straight line that joins 2 points on the circumference. That means if I draw a line from here to this point, this line is a chord. If I draw a line from this point on the circumference to this point, this is also a chord. Anyhow I draw it, any orientation, that line is a chord. So I write chord here and I write chord here. Now for the next on our list, we'll talk about diameter. So diameter is simply a chord that passes through the center of the circle. So if this is the center of the circle, you have a chord that passes through the center of the circle, then that chord is called a diameter. The next on our list is what we call an arc. So I'll draw a circle to show you an arc. An arc is simply a portion of the circumference. So say if I cut the circumference into parts, the individual parts will be an arc. So I can see from here to here is an arc. So if I'm drawing this by itself, it will look like this. So this is an arc. And this portion is also an arc. All of it is also an arc. If I cut it this way, this portion is an arc. So if you cut the circumference into any particular portion, you have an arc, right? So in this case, I cut it into this portion, this portion, this portion. This is an arc. This is also an arc. This is also an arc. The next one, this is what we call a sector. Let me draw another circle so that I can illustrate the remaining ones to you. A sector is simply created when you have a radius and another radius, and you have an arc that bounds them. So what this means is that a sector is kind of like dividing a circle from the center of the circle. See, I divide this circle from here. This area here is a sector. This area here is a sector. This area here is a sector. Whenever you have a portion of the circle bounded by 2 radius and an arc, you call that portion a sector. So this is a sector. This is a sector. This is a sector. A sector by itself looks something like this. So this is a radius. This is a radius. This is the arc. The next one we talk about is a segment. Now, if I were to draw a chord that divides the circle into 2 parts, this is a chord, this will be a segment, and this will be a segment. So whenever I draw a chord that divides the circle into 2 parts, the areas, respective areas of the parts, are segments. The next step is what we call a tangent. The tangent is simply a line drawn that touches the circle at a single outer point of the circle. So this line is a tangent. If you also have the line like this and it touches the circle on a single point, we call this a tangent. For the last one, a secant. A secant is kind of like an overextended chord. So let me clean up space for me to draw the secant. So say you have a circle here. The secant is simply a line that passes through the circle. So this is a secant. This is also a secant. So that's it on the parts of the circle. Let's move on to the theorems of the circle. So the first theorem on our hands is we are told that a straight line from the center of a circle that bisects a chord is at right angles to the chord. What this means is if we have a circle and let's say this is the center of the circle and we also happen to have a chord here. If we have a straight line from the center of the chord and this straight line happens to bisect, what it means to bisect is to divide a line into two equal parts. So if you bisect this chord, what this theorem is basically telling us is that the angle between the radius and the chord will be a 90 degrees angle. And what this also means is that the distance from this point to this point is also equal to distance from this point to this point. So let's solve some examples to help you understand this theorem better. The example of this theorem is that we are told that in a circle with center O and radius 10 centimeters, this is 10 centimeters, a chord AB is drawn such that the perpendicular distance from O to the chord is 6 centimeters. We are told that we should calculate the length of the chord, and 2, if another chord CD is 12 centimeters long, find the perpendicular distance from the center O to the chord CD. So first of all, I'll write out solution here. Secondly, I'll try to interpret this question into a circle. Okay, so I'll draw out my circle here. Say this is my circle. I are told that in a circle with center O, let's say this is the center of our circle, that center is called O, and radius 10 centimeter. So the radius of this circle is 10 centimeter. A chord AB is drawn. So the name of the chord is line AB. I'll draw a chord here. If I draw a chord, let's say this is the chord. So I'll call this AB. Now the chord AB is drawn such that the perpendicular distance from O, perpendicular simply means a 90-degree angle distance. So what they are telling us here is that the perpendicular distance, which is a straight line that bisects this chord AB, is 6 centimeters. So this is 6 centimeters. We are told to calculate the length of the chord. That means we are told to calculate the total length from A to B here. So let's find length of chord. Now, how do we find length of chord? We can use the idea of triangles to find length of chord. Now, remember that the radius of this circle is 10 centimeters. So from here to here is 10 centimeters. From here to whatever part of the circumference is 10 centimeters. From here to here is still 10 centimeters. So that if we pull out this triangle here, we have something of this nature. Something like this, like this, like this. And then you have the line O that connects to AB. So if I name the parts, this is point O, this is A, this is B. And this is 10 centimeters, this is 10 centimeters, this is 6 centimeters. This is a right angle triangle, this is a right angle triangle. And then we are looking for the whole distance from here to here. Let's call that distance L, right? So we can use the idea of a Pythagoras theorem to solve this. So if you use one of the triangle here, let's say this distance is X, so that our new triangle looks like this, 10 centimeters, and then 6 centimeters here. So this will be X. Now, if you want to find X using Pythagoras theorem, you simply say the square of the hypotenuse plus the square of the other two sides. So using Pythagoras theorem, so first find x, we simply say 10 square is equal to 6 square plus x square. 10 square is 100. This is equal to 6 square is 36 plus x square, still x square. So making x square subject to formula, we have x square is equal to, we move plus 36 over to the other side, we have 100 minus 36. X square is equal to 100 minus x6 is 64. So if we take the square root of both sides, this is x is equal to 8 centimeters. Now if x is equal to 8 centimeters, what's the relationship between x and L? Remember, I said the line from the center bisects the chord. To bisect means to separate to two equal parts. That means this part is equal to this part. So that means that the length of the chord is equal to 2x. Okay? Because if you sum x here plus x here, you get L. So the length of the chord is equal to 2 times 8. 2 times 8 is equal to 60 centimeters. So we are done with the first example. Now for the second example, we are told that if another chord CD is 12 centimeters long, find the perpendicular distance from the center O to the chord CD. Before we do that, let's clean up space. If we redraw the circle, you have something like this. And then in this case, we are told that another chord is CD, which is 12 centimeters long. Let's say the chord is here, and let's call the chord CD. Let's say this is the center of the circle. According to the question, the complete distance from C to D is 12 centimeters. So that means here to here is 12 centimeters. Now the radius of this circle is simply 10 centimeters. From what we know, this is 10 centimeters. And then this is point O. We are told to find the distance, the perpendicular distance from O to CD. So that means the line that bisects chord CD. So let's call this distance D. Now I can extract this triangle. If I extract this triangle, it looks like this. This is line CD. This is point O. This is the distance we're looking for. This is 10 centimeters. This is 10 centimeters. Now from here to here, that we know is 12 centimeters. So how do you know the distance from here to here? Remember, distance from here to here is half of the total distance of the chord, because the chord has been divided into two equal parts by the perpendicular line. So this is 6 centimeters. This is 6 centimeters. We can use Pythagoras theorem to find distance D. So that using Pythagoras theorem here, we see the hypotenuse square, which is 10 square, is equal to the sum of other two side squares. The two other sides is this side and this side. That means this will be D square plus 6 square. So that if we make D square subject to the formula here, we have D square is equal to, you have 10 square here. We are moving 6 square to the other side, becomes minus 6 square, and that is equal to 10 square is 100 minus 6 square is 36. This is equal to 100 minus 36 is 64. That means that D square is equal to 64. I get D square root of D square is equal to square root of 64. So if I take the square root of this place, I have D. This is equal to, taking the square root of 64, I have 8 centimeters. So the perpendicular distance from the center O to point CD is 8 centimeters. That's it about this theorem. The questions are not really hard to solve once you can draw out the problems like this and identify how to use the Pythagoras theorem. You will be fine. So let's move into the next theorem. The next theorem is saying the angle subtended at the center of a circle is twice that subtended at the circumference. Now let me show you a demonstration of this theorem. See, we have a circle. Now there's a keyword I would like you to understand here. Whenever you're told that an angle is subtended, you need to think of three things. Number one, a chord. Number two, an arc. Number three, a segment. This part is very, very important in really understanding how to solve circle theorem problems. Now, for a chord to subtend an angle, if I have a chord and an angle is created from that chord, let's say this is my chord and an angle is created from this chord. If you notice, the line joins at the edges of the chord. So here I'll simply say my chord subtends an angle theta. Now I could also say this same chord also has an arc. So the arc in play here is this arc. So this arc also subtended this angle. The segment here, we have two segments here. You have segment 1 here and we have segment 2 here. This segment has an angle of theta. This segment does not have any angle here. Okay, so whenever an angle is created, you have to check where it is created from. That is what will help you understand this theorem. Is it created from the same chord? Is it created from the same arc? Is it created on the same segments? Let's look at how this works for this theorem. So say I have a circle and say this is the center of the circle. If I have an angle subtended at the center of the circle, let's call this angle theta. Now this angle is subtended by an arc here. If this same arc subtends an angle on the circumference, notice that where the angle is coming from is from this arc. Now this same arc subtends an angle on the circumference. Let's call that angle alpha. What this theorem is simply saying is that whenever you have the same chord, the same arc obtaining an angle on the center at once and on the circumference at once, it simply tells us that the one at the center is equal to 2 times the one at the circumference. That means if you multiply this angle by 2, you get this angle. So if this angle was, say, something like 20 degrees, the angle here will be equal to 40 degrees. So let's look into examples to help you really understand this. But before we even look into the examples, I want to start looking at where angles come from in the circles before you start solving questions. So let's jump into the question. We have 2 questions on our hands. The first is that we are told to find angle BAC here. This is angle BAC. Now, first find angle BAC, we say for BAC. If you notice, this arc here is responsible for subtending the angle at the center and at the circumference. So we use our theorem here. We know that the angle subtended at the center is twice the angle subtended at the circumference. So that we say angle B, the center is O. So we can say angle BOC. So I'll say angle BOC is equal to 2 times angle BAC. The reason is that angle at center is equal to 2 times angle at circumference. So that angle BOC is giving us 80 degrees. So this is 80 degrees is equal to 2 times, we do not know angle BAC. So that's what we are looking for. So angle BAC, if we make angle BAC the vector formula here, we divide both sides by 2. So that BAC is simply equal to, this cancels out this here, 80 divided by 2 is 40 degrees. Now this is the answer of angle BAC. Now let's go to the next example. For this question, we are close to find angle BAD. That's a mistake. This should be BAC. Let's call this angle theta here. So let's say this is angle theta. We are close to find angle BAC. So I'll say for BAC. First of all, BAC is this angle. BAC is this angle. So I'll try to look at where the angle comes from. So the angle comes from this point, and the arc that subtends the angle is this arc here. So I'll also look at other angles that the arc subtends. The arc happens to also subtend an angle at the center of the circle, and that angle is 100 degrees. So we know that the arc subtends that angle at the center of the circle and at the circumference. We can now use our theorem. So from that theorem, we can say we know that angle BOC, which is the angle at the center, is equal to 2 times angle BAC. Okay, so this is BAC. The reason for this is angle at center equals 2 times angle at circumference, where angle BOC is given as 100 degrees. So we can say this is 100 degrees is equal to angle 2 times angle BAC. So that angle BAC is equal to 100 divided by 2, and that is equal to 50 degrees. We found angle BAC. So for angle theta, we can also use the theorem to find angle theta. Angle theta is simply this angle here. If you notice, the arc at play here that forms angle theta is this arc. Arc from here to here. So this arc forms an angle at the center, and it also forms an angle at the circumference. Okay, so the angle at the center here for this arc is theta, and the angle at the circumference is 130 degrees. Let me clean up space. So this simply tells us that theta is equal to 2 times the angle at the circumference, which is angle BDC. So angle BDC. The original angle BDC to be 130 degrees. So theta here is equal to, you're looking for theta by the way, so this is for theta. So theta here is equal to 2 times 130 degrees. 2 times 130 degrees is equal to 260 degrees. We could have also find theta by using angle at the point. What that means is that if we pick out the center of this circle, it looks more like this. Here is a 100-degree angle here, and there's a theta angle here. So we can use the idea of theta plus 100 is equal to 360. And our reason will be angle at a point. So essentially, this is method 2 of solving this. So this angle at a point, and then we can say theta here is equal to 360 minus 100. This will be 260 degrees. So you can think of this as method 1 of finding theta here and method 2 of finding theta here. So we also have extra questions on this theorem. Let's look into them. So for the next set of examples here, in this case, we are told to find theta for this example. Now, you might want to pause the video and try to solve it yourself. So I would like you to pause the video and try to solve question 3 and question 4 by yourself. So we'll start with question 3. Like we did before, we look at where an angle is coming from. Now we're told to find angle theta. This is angle theta. Now angle theta is coming from this arc here. The next question we ask ourselves is that what other angle is this arc producing? Now this arc is also subtending an angle at the center, but we do not know that angle that it is suspending. So we know that the angle here is AEC, and we do not know the angle. So for us to be able to find theta, we need to find angle AEC. So for theta here is simply equal to, for theta, we know that angle AEC is equal to, that's the angle at the center is equal to 2 times theta. Okay, so that is the reason is angle at center is equal to 2 times angle at circumference. But we don't know angle AEC and angle theta. For us to get angle AEC, we need to use angle at the point to get angle AEC here. If you look at the center of the circle, for us to get angle AEC, it looks something of this nature. This is A, this is E, this is C, and then we know the outer part of the angle here. So this is 300 degrees. For us to get here, we simply use the idea of angle at a point. So the angle at the point is simply saying AEC plus 300 degrees is equal to 360 degrees here. And the reason for this is angle at the point. So that we can say AEC is equal to 300 moving to the other side is 360 minus 300. 360 minus 300 is simply 60 degrees. So that now that we know angle AEC at 60 degrees, we can use the first equation here and say, let me clean up this space. So from what we know, angle AEC is equal to 2 times theta. So using this equation, we know that theta is equal to AEC divided by 2. So we simply plug in 60 here. That means that 60 divided by 2 is equal to 30 degrees. So that tells us that theta here is equal to 30 degrees. So this is the value of theta here. For this question also, you can try to pause the video and solve the question. So in this question, you have to be careful the way you solve it. So the first thing we want to do is write out solution. You're looking for theta, so I'll look at the arc that creates theta. Now the arc that creates theta is this arc. And this arc also creates an angle here. We do not know the value of this angle. So finding the value of this angle can help us find theta. But we're also given an extra information that is really, really important. Now we know that the distance from here to here is equal to the distance from here to here. This tells us that we have an isosceles triangle, and this angle is given so that if you extract this triangle, it looks something like this. This is an isosceles triangle. This is a 38 degrees angle here as given here. Now this is a 38 degrees angle. This side must be a 38 degrees angle based on isosceles triangle. So here angle CAV is also 38 degrees. Now that we know that, to find theta here, we can say theta is equal to, that's the angle at center, is equal to 2 times angle at circumference. Angle at circumference is angle CAB. So we know that angle CAB is 38 degrees, so that theta is simply equal to 2 times 38 degrees. So theta here is equal to 2 times 38 is equal to 76 degrees. So that's the value of theta here. So for this particular theorem, you have to be wary. You have to note where the angle comes from, and you have to trace it back and forth to be able to solve your questions. So let's move on to the next theorem. The next theorem is simply saying that angles in the same segment are equal. To really see this at play, let's draw a circle. Say I have my circle here, and I have a chord that separates the circle into segments. Remember, this is segment 1. Let's call this segment 1, segment 2, segment 2. So that if I have an angle subtended from this chord here onto the circumference here like this, and we also have another angle subtended from this same chord onto the circumference like this, and we also have an angle subtended from this same chord onto the circumference like this. Let's say that this angle is angle A, this angle is angle B, this angle is angle C. But notice one thing, all of them are in the same segment. If you were to take a protractor and measure the angles here, we'd find out that angle A would be equal to angle B, would be equal to angle C. The reason is that they are in the same segment. So this passes on the idea that angles in the same segment are equal. The same thing happens to this segment. First, have an angle like this from this same chord, an angle from this same chord. Let's call this angle angle E, and this angle D. If you were to measure these angles, you find out, because they are coming from the same point onto the circumference, you find out that angle E is also equal to angle D, and they are also in the same segment. The point is, anytime we have two angles coming from the same arc or chord, and they are in the same segment, those two angles are equal every single time. So you have to take note of this. Let's look at examples for you to understand better. So this example is clearly given here, and then for this one we are told to find the angle theta and angle alpha here. The first thing we want to do is to look at angle theta and look at where angle theta is coming from. So angle theta is coming from this point here and this point here. So the arc of concern is this arc, right? Now we know that if an angle is being subtended from the same arc or chord from another angle, those angles are equal, okay? So if we want to look for another angle that's subtended from this same arc, another angle like that is this angle, okay? So from here, we can say for theta, For theta here, we know that theta here is equal to this angle here, which is angle CAD. Now, angle CAD here is simply 40 degrees. The reason for this is angle in the same segment. So here we can simply say theta is equal to 40 degrees. We've gotten our angle here. The next thing we want to look at is angle alpha. So for alpha, we know that alpha is this angle. So we want to check where alpha comes from. Now, alpha comes from this line and this line. So the arc of interest on alpha is this arc here. Okay, so we want to look at what other angle does this arc create. Now, if you notice, the arc creates this angle here too. So this angle here, the same segment. If you notice, you can also divide this into segments here, can divide them into segments here. But your point of interest should be, where does the angle come from and what other angle does it create? Okay, so let's move on to the next example. Now you can try to pause the video and solve this one yourself. But like we did before, we look at the first one. We say for alpha. So we look at angle alpha. Angle alpha comes from this arc here. So the arc of interest is from here to here. Okay, so this is what creates angle alpha. Now, what other angle does this arc create? It creates angle theta, but we do not know angle theta. It also creates the angle at the center. Okay, so we can use our first the theorem we know before. We know that angle at center is 2 times angle at circumference. So what this tells us is that 84 degrees, which is the angle at center, is equal to 2 times alpha. So the reason for this is angle at center is equal to 2 times angle at circumference. So that for alpha here, we can say alpha is equal to 84 divided by 2. So 84 divided by 2 is 42 degrees. Now the next thing we are asked to find is b theta. So for theta here, the arc subtending theta is this arc. So we can simply say theta here is equal to alpha because they come from the same arc. This tells us that theta is equal to alpha. And if theta is equal to alpha, the reason for that is angle in the same segment. So theta here is equal to, with original alpha to be 42 degrees, so this will be 42 degrees. So let's look at more complicated problems under this theorem. Now you can pause the video and try to solve this one yourself and this one yourself. So let's start with question 3. If you are told to find theta here, like we did before, we look at where theta is coming from. So if you notice, the line that theta is coming from is this line and this point. Okay, so this is the arc of interest for us. We also look at what other angles is this arc making with the circumference or the center. It's not making any angles with the center, but it's making another angle with the circumference, which is 31 degrees here. This one is totally different, so we ignore it. So to get our value of theta, we already know this angle, so we can simply say for theta here is simply equal to angle EBD. So angle EBD for 31 degrees. And the reason for this, our angle in the same segment. Okay, so we know that theta here is simply equal to 31 degrees. This is pretty straightforward. Now let's look at this example here. We're told to find angle theta here. Angle theta starts from this arc, like this, and this is a diameter line. Where the arc of interest here is this arc. So we look at other angles that the arc suspend. If you look at this angle, we notice that we do not know, there's nothing given here, so we cannot use it to tell theta. We also notice that this angle isn't of much help when finding theta either. But since we are dealing with the diameter, there's something that simply comes in handy. This arc makes an angle with the center. Now this is a straight line, so this angle is simply 180 degrees. And this angle is simply 180 degrees. Okay, so the arc here makes an angle of 180 degrees with the center. So we can use it to tell theta. So we can say for theta here, you can say angle at center, which is 180 degrees, is equal to 2 times theta. Now, 2 times theta is simply, the reason for this is angle at center. So I can write it like this. At center is equal to 2 times angle at circumference. So this simply tells us that theta is equal to 180 divided by 2. 180 divided by 2 is 90 degrees here. So that's it for this particular theorem. Let's move on to the next theorem. For this theorem, we are told that angle in a semicircle is a right angle triangle. Now what this translates to is simple. Say we have a circle and we happen to divide the circle. Diameter is what happens to subtend an angle instead of a regular chord. This diameter will subtend an angle here on the circle. This angle will be a 90-degree angle every single time. So if you also have another angle here subtended from the diameter, it will be a 90 degree. As long as this line passes through the center, whatever angle is being subtended from the diameter here will be a 90-degree angle. So if we do that here too, this will be a 90-degree angle. If you do that here, this will be a 90-degree angle. Now, in this case, we are told to find theta. So we can say here for theta, if you notice, theta is this, the angle of the arc of interest is this arc. Now, if you look at this arc, it creates an angle at this point. There's no other thing that can help us here. But we know that angle in a semicircle is a 90-degree angle. So that tells us that this angle is simply a 90-degree angle. If this angle is a 90-degree angle, we can use the idea of a triangle to find angle theta. Okay? So how do we do that? We simply say 43 plus, we simply say 43 plus angle. Now we're not given this angle from the onset, so angle ABC, angle ABC plus angle theta is equal to 180 degrees. Reason for this is angles in a triangle. Okay, now we don't know ABC from the onset, but we know that ABC is equal to 90 degrees. Reason for this is angle in a semicircle. So that we can plug in 90 degrees into this equation, and we have 43 plus 90 plus theta is equal to 180 degrees. If we add 43 and 90, we have 133 degrees plus theta is equal to 180. So that if we move 133 to the other side, we have theta is equal to 180 minus 133, which is equal to 47 degrees. So theta here is equal to 47 degrees. Now for this case, we are also told to find theta. You can pause the video and try to solve it yourself. So here I'll simply say for theta, if you notice the angle from the center, the angle subtended by this diameter here is this angle. So this angle is the 90-degree angle. So for theta here, we use the idea of angles in a triangle still. So we can say 22 degrees plus angle BAC plus theta is equal to 180 degrees. So the reason for that is angle in a triangle. Now we also know that angle BAC is equal to 90 degrees because it is angle subtended by the diameter. Okay, so this is the reason is angle in a semicircle. So that if you plug this into this, you have 22 plus 90 plus theta is equal to 180 degrees. 22 plus 90 is 112 plus theta is equal to 180 degrees. Now theta here is simply equal to 180 minus 112 degrees. So 180 minus 112 degrees is degrees. So the value of theta here is 64. So that's it for angle in a semicircle. I don't think you need too much examples to really understand it. The main idea is that when you have a diameter subtending an angle, the angle that is subtended on the circumference is a 90-degree angle. So let's move on to the next theorem. This next cycle theorem states that opposite angles in a cyclic quadrilateral are equal. What this simply means is that if we have a circle and we happen to have a quadrilateral inside the circle, so a quadrilateral simply means a four-sided polygon, something that looks like this, like this, like this, like this. So this shape inside the circle is a quadrilateral. Now what this theorem is simply saying is that the opposite angles, say I have here as theta and I have here as alpha, and say I have here as w and I have here as v. This theorem is simply saying the opposite angles of theta and alpha, if we add them up, they'll be equal to 180. So this will mean that theta plus alpha will be equal to 180. And it also means that the opposite angles of w plus v will also be equal to 180. So anytime you have a four-sided shape like this inside a circle, the opposite angles, if you sum the opposite angles, it is equal to 180. Now let's look at examples for you to understand this better. The first example here, we're told to find alpha and theta. So to find theta, let's first find theta. So I'll say for theta here. Now if you notice, theta is in a quadrilateral. So we have a four-sided shape here. Now how do we get theta? We can use our theorem, which is the opposite angles of a cyclic quadrilateral are equal. So the opposite angle of theta here is 68. That would simply mean that theta plus 68 is equal to 180 degrees. The reason is that opposite angles of a cyclic quadrilateral are supplementary. So abbreviate this. This would mean that theta is equal to, if I move 68 over to the other side, I have 180 minus 68. So from here, 180 minus 68 is equal to 112 degrees. From here, we can find the value of alpha by doing the same thing. So the value of alpha here, we'll check for the opposite angle here. So I'll say for alpha, we still do the same thing. You look at the opposing angle in the quadrilateral. So the opposite angle in the quadrilateral is 102 degrees here. That would mean that alpha plus 102 degrees is equal to 180. The reason is because the opposite angles in a cyclic quadrilateral are equal. There's no space, so I will not write that here. So that alpha is equal to 180 minus 102. 180 minus 102 is equal to 78 degrees. So that's my value for alpha. For the next example, you can pause the video and try to solve it yourself. So like we've been doing before, we are told to find theta in this case. Now for us to find theta, we have to know what we are dealing with. So I'll try to interpret the whole circle similar. Now first of all, we have a cyclic quadrilateral here, and we're told to find theta. If you're told to find theta, we know that opposite angles in a cyclic quadrilateral are supplementary. That means if we add the angle for the totality of here with this theta, we get equal to 180 degrees. The problem is we know the angle for here, but we don't know the angle for this side. So can we get that angle? Yes, we can. Now, if you notice, this is the center of the circle and this is a radius, this is a radius. So that means this side is equal to this side. If this side is equal to this side, that means we have an isosceles triangle in our hands. Let's call this angle alpha. Since we have an isosceles triangle here, for angle theta, first of all, say for theta, we have to find alpha. So for us to get alpha, we'll say alpha equal to 38. Why is alpha equal to 38? Because this side, the length of this side is equal to the length of this side. And we have an isosceles triangle. So I have an isosceles. Now that we have our value of alpha, we simply know that the angle here is the sum of 48 plus alpha. So that would simply mean for us to get our theta, we use our circle theory. Our circle theory simply says the opposite angle, which is theta plus 48 plus alpha, is equal to 180 degrees. So the 180 degree is, the reason for this is cyclic quadrilateral. So this is an abbreviation of the total reason here. Now, my theta here is simply equal to 180 minus, if I move 48 and alpha to the other side, it becomes 48 minus alpha. And then this is equal to 180 minus 48 minus alpha is 38. This way 38. And then theta here is equal to 180 minus 48 minus 38 is equal to 94 degrees. Theta here is equal to 94 degrees. Now, this is simply it for this theorem. We are going to look at, let's look into the next theorem. For the next theorem, we are told that the angle between a tangent and a radius at the point where the tangent touches the circle is a right angle. What this theorem simply says is that, say you have a circle, and of course, let's say this is the center of the circle. If you have the radius of a circle drawn from this point to the point where the tangent makes contact with the circle, this angle here is a 90-degree angle. So that's what this theorem is simply saying. So whenever you have a tangent line, say you have a tangent line here and you have a radius line touching the tangent line at that point of contact, this angle will be a 90-degree angle. So let's quickly look into examples for you to get the idea down. So for the first example here, we are told to find theta. Now, if you notice, this is the center of the circle. The center of the circle has a radius and touches the tangent at this point. So based on our theory that says if the line drawn from center of the circle makes contact with the tangent, you get a 90-degree angle. So this angle in its totality is a 90-degree angle. If this entire angle is a 90-degree angle, that simply means that theta plus 48 is equal to 90 degrees. Now, the reason for this is because the tangent line makes contact with the radius. So that theta here is equal to, if I have 90, this one goes to the other side, becomes minus 48 degrees. So this is 90 minus 48 degrees is 42 degrees. So theta here is simply equal to 42 degrees. For this question, I want you to pause the video and solve it yourself. So like we've been doing before, we try to simplify the question because it looks somehow complicated. But here now, if you look at this very, very closely, you notice that there are two lines that indicate that the angle here, let's call the angle here alpha, and the angle here are the same thing. So if you have these two lines, simply tells you that this angle and this angle are the same thing. And that means you have an isosceles triangle. Now, based on our theorem, we know that if we have the tangent touching the radius, now this is the center of the circle, so this is a radius line. So that means this line to this point is a 90 degrees angle. We are not giving any value here, but what we know is that angle in a semicircle, now if you look at this, this is a semicircle. From what we know is a 90-degree angle. So this angle is a 90-degree angle. If this angle is a 90-degree angle, we can use it to get alpha and then use it to get theta. So from here, we'll say 90 plus alpha is equal to 180 degrees. The reason for this is the sum of angles in a triangle. So from here, I can get 90 plus 2 alpha. Alpha plus alpha is 2 alpha. So this is equal to 180. From here, 2 alpha is equal to 180 minus 90. So 180 minus 90 is simply 90 degrees. So what I have is 2 alpha is equal to 90 degrees. So from here, I can divide both sides by 2 so that alpha becomes equal to 45 degrees. Since I know alpha is 45 degrees, that means I can get my theta here. Now, how can I get my theta? I simply know that I'll carve out space here, solve this. I simply know that theta plus alpha is equal to 90 degrees. Now, the reason is because I have my tangent line to radius. So this is factorized tangent to radius. This is abbreviated. So from here, I know simply that if I want to find the value of theta will be equal to, I move alpha to the other side. This is 90 minus alpha, and this is equal to 90 minus alpha is simply 90 minus 45. 90 minus 45 is simply 45 degrees. So my theta here it's 45 degrees. Now, that's it for this theorem. Let's look into another theorem. For the next second theorem, we are told that two tangents drawn from a point to a circle are equal. Now, to simply explain this to you, say we have a circle, and then I decide to put a point anywhere around the circle, as long as it is not inside the circle. So let's say we decide to put a point here. What this theorem is simply saying, if we have a tangent from this point, and we have another tangent from this point, the two tangent makes course back to the circle. Let's say this is the exact point that happens, and this is the exact point that happens for this tangent. Let's call this line A, B, C. If you were to measure the line length of CV with a ruler, and you measure the line length of DA with a ruler, it will be equal to each other. So that's what this theorem is simply saying. To see how this looks like when we are using it to solve problems. So we already have an example on the screen, and in this case, we are meant to find theta. I did not write it, but here we are meant to find theta. Now you can pause the video and give it a try if you want to. But let's quickly jump into it. Based on our theorem, we have a tangent here. And what do we know about a tangent from an external point? A tangent from an external point is equal to each other. That means this line is equal to this line. What do we do with that information? We can separate this into two triangles. Another theorem that's also working here in this question is that the tangent makes contact with the radius. So that tells us that this entire angle is a 90-degree angle. And this entire angle is a 90-degree angle. Okay, so when the tangent line makes contact with the radius, we have a 90-degree angle. Since we are told to find theta, a very, very helpful way we can find theta is to find the angle at the center so that we can find the angle at the circumference. Remember, the arc in question here is this arc. The arc suspends this angle on the center, so the angle it suspends on the circumference is the theta. So how do we find this angle? We can find this angle by finding this angle here and this angle here. So how do we even find this angle? If we divide this thing into two, this will be 30 degrees here. This will be 30 degrees here. Okay, so if this is 30 degrees, this is 30 degrees, I will bring out the triangle. We have something like this. This will be 30 degrees. We don't know this angle, but that's what we're looking for here. Let's call it alpha. If we call this alpha, this will also be alpha. Okay, so that the angle here will be 2 alpha. So let's call this alpha, and then the angle we know here to be 90 degrees. So for alpha, I'll say for alpha here, this will simply mean that we add everything inside the triangle. So for everything inside the triangle, I'll say alpha plus 90 plus 30 is equal to 180 degrees. And the reason for this is the sum of angle in a triangle. Okay, so from here we have alpha plus 90 plus 30 is 120. This is equal to 180. So alpha here is equal to 180 minus, if I move 120 to the other side, it becomes a minus. This is 120, and then 180 minus 120 is 60 degrees. So I have my alpha as 60 degrees. Now my angle here is the 2 alpha. Just to clarify this image, the new circle would look like this based on what I've solved so far. So from here, this is theta. Now I know my alpha now to be 60 degrees. All right, 60 degrees here. This is 60 degrees. This is 60 degrees. So for me to get theta, remember I have to get here. So how do I get the angle there? The angle there, let's call it COB. So angle COB, I'll say for angle COB. How do I get angle COB? This is the center, so I'll use angle at the point. So angle at the point here is simply COB plus alpha plus alpha. And angle at the point is simply equal to 360 degrees. So the reason for this is angle at the point. So if this idea here is not clear to you, whenever you have a point and there are several lines crossing the point. Say this is alpha, this is beta, this is W, this is H. If you sum the angles around the point, the value is equal to 360 degrees every single time. Okay, so the same thing for here, that's what we apply here. So angle COB plus 2 alpha is equal to 360 degrees. So this is COB is equal to 360. If you move 2 alpha to the other side, it becomes minus 2 alpha, and this is equal to 360 minus 2 open brackets. Alpha is 60, so there's 60. This is equal to 360 minus 2 times 60 is 120. So angle COB here is 360 minus 120. That's equal to 240 degrees. So COB here is 240 degrees. So that means the angle here is 240 degrees. If the angle here is 240 degrees, remember the arc we are looking at is this arc, and it makes 240 degrees be the center. And this is the same arc that happens to make an angle with this circumflex here. So how do we get this angle here? Let me clean up space. So for us to get this angle here, we simply apply the idea that angle suspended at the circumference is twice the angle suspended at the center. So this simply means that 240 degrees here is equal to 2 times theta. Okay, the reason for this is angle at center is equal to 2 times angle at circumference. This simply means that 240 is equal to 2 times theta, which is 2 theta. So theta here is equal to 240. If I divide both sides by 2, so 240 divided by 2, 240 divided by 2 is 120 degrees. So theta in this example is equal to 120 degrees. Now let's look into next theorem. We are going to still look at something like this later on to help you understand it. For the next theorem, this theorem is often called the alternate segment theorem. The next theorem simply states that the angle between a tangent and a chord, is equal to the angle in the alternate segment. To really understand this, I'll show you how it looks like in a circle. So let's say we have a circle like this, and we also happen to have a tangent to the circle. Remember, the tangent makes a contact to the circle at a single point. So let's say at that point where it makes contact to the circle, we have a chord on that point. Once you have a chord in a circle, you have a segment. So this side is a segment, and this side is also a segment. What this theorem is simply saying is that if the tangent forms an angle with this segment of the chord, so if I have this segment of the chord, any angle formed in the other segment will be equal to this angle. So if this angle is theta, that means if this chord were to form another angle in this segment, it will be the same thing. So if I were to draw an angle like this, this angle will also be equal to theta. Remember, what is suspending the angle is the chord, right? So if this chord in particular that makes an angle with the tangent is to suspend an angle in the other segment, it will be equal to this angle. If it happens again here, this will also be equal to theta. Again, if you want to see it from another angle, this is a chord still connecting to that point where the tangent makes contact to the circle. What happens with the chords? That segments are created. So if you are considering this chord now, we have a segment here. So I'll call this new segment. Let's say we also have a segment here, right? This is a new segment. So remember, the dividing line between the two new segments is this line, right? So I will have an angle in the segment making with this tangent here. Let's say this angle is alpha. Now, if this chord were to also suspend an angle on the other segment, on the other new segment, which is this side, any angle it suspends here will be alpha. So if you notice, this chord suspends an angle of this here. So that means this angle here will be alpha. So to really see this actually, let's look at examples. So for the first example, you can try to pause the video and solve it yourself. we jump into it directly. So what we have here is a tangent making an angle with a chord. Okay, so as it makes an angle with a chord, we are told to find angle theta here. Now, what do we know about this angle it makes? The chord and the angle inside the circle. You look at the circle, this is the angle in a semicircle. Look at the circle, we have a diameter line here making an angle with the circumference. So that means this angle is automatically a 90 degrees angle. If this angle is automatically 90 degrees angle, so we can find theta by finding all the angles in this triangle. So for us to jump into finding theta, we'll say for theta, let's call this angle alpha. So how do we find angle alpha? We can find angle alpha using the idea we just looked at now. Look at this tangent here. Look at this chord here. It makes an angle of 7 degrees with this tangent. It's on the alternate segment circumference. It makes an angle of alpha. So that simply tells us that alpha is equal to 77 degrees. The reason for this is angle in an alternate segment. We knew that the angles in a triangle is 180 degrees. So we simply just come here and say theta plus alpha plus 90 is equal to 180 degrees. The reason for this is sum of angles in a triangle. So that from here, I can say theta is equal to, if I move alpha and 90 degrees to the other side, I have 180 minus alpha minus 90 degrees. So this is equal to 180 minus alpha is 77 degrees, so this is 7 minus 90 degrees. If I have 180 minus 77 minus 90 degrees, this is equal to, that simply tells us that theta is equal to 13 degrees. Now, for the next example, you can also pause the video and try it solve it yourself. For this example, if we look at the tangents, we look at what we're looking at, which is theta. You know that theta clearly makes an angle with the tangents here, and it works on a chord. So if you notice the chord, it separates the circle into two segments. This segment here and this segment here. Now, this chord directly makes an angle with the circumference of the other segment, and that angle is 40 degrees. So what that simply tells us here is that for theta, we can simply say theta is equal to 40 degrees directly. The reason for this is angle in the alternate segment. So that's it for this theorem. Let's look into the extra section of this video, where we'll be talking about multiple examples that deal with multiple theorems at a time. Now, for the first example in our extra example section, we are given this circle and we are told to find the value of theta. Now, from the value of theta, we look at the circle we are given and try to find out things that can help us get our value of theta. If you notice the value of theta, theta clearly makes an angle with a chord. Now, this chord separates the circle into two segments. This segment here and this segment here. Now, since it separates the angle into this segment, let's look at whether this chord suspends an angle on the circumference of this circle. So if you look at this chord, it suspends an angle on this circumference here. Okay, so let's call the angle alpha. We don't know the angle, but we do know that the chord suspends an angle with the center of the circle, and that angle is 40 degrees. So because suspending an angle with the circumference and with the center of the circle, we can know the angle and the circumference. Okay, so for us to get alpha first, first of all, the question is saying we should find theta. So I'll say for theta, but to get theta, we have to get alpha. So I'll say for alpha under for theta. So for alpha here, we'll simply say 40 degrees is equal to 2 times alpha. The reason for this is simply the angle at center suspended by the chord is equal to 2 times the angle at circumference. So angle at center is equal to 2 times angle at circumference. So that means that 40 degrees here is equal to 2 alpha. If I divide both sides by 2, alpha is simply equal to, this cancels out this, 40 divided by 2 is 20 degrees. So alpha is 20 degrees. Now, since I know my value of alpha, I can quickly get my value of theta here. My value of theta is equal to 20 degrees. Now, the reason for that is theta. So therefore, theta is equal to 20 degrees And the reason for that is angle in the alternate segments. So that's it for this question. Let's go to the next example. Anytime you see a question, my advice to you is to start from where the theta is, or the given value you're looking for is, and try to relate it to other parts of the circle. Okay, so let's move into the next example. So for this example, you can also pause the video and try to solve it yourself. In this question, you are meant to find theta. So I'll say find theta here. I didn't write it before. Now, if you look at this question, what we're looking for is this angle here, theta. But we have many connections to angle theta, so we have to tread cautiously. Now, if you look at this angle theta here, if we try to relate it to what we are given, this is the arc that suspends angle theta, and this arc also happens to suspend an angle at the center. Let's call this angle alpha, because if we know angle alpha, we can know angle theta. Since we cannot know angle alpha at the moment, we are given 102 degrees. So how can we work from 102 degrees? When you have tangency linked to a circle from a point, simply means that the length of this tangent here is equal to the length of this tangent here. And another theorem also says that if the tangent makes contact with the radius of the circle, this is the center of the circle, by the way, this will be a 90 degrees angle, and this will be a 90 degrees angle. Okay, if we get the angle here, let's call this angle beta. Okay, well, how do we get angle beta? For us to get angle beta, it is important you know this. Whenever we have lines crossing each other, if this angle is 100 degrees, this angle will also be 100 degrees. And if we don't know this angle, we can name this A, we can name this angle A. So that if we use the idea of angle at a point, we simply say A plus 100 plus A plus 100 will be equal to 360 degrees, which is angle at a point. That's what still happens here. This angle is 102 degrees. This angle will be 102 degrees. And if this angle is beta, this angle will be beta. So that's for us to look for beta first, to say for beta, remember the key thing here we are trying to look for is theta, no beta. So you start from beta. For beta, we simply say beta plus, this is angle at a point, so 102 degrees plus beta plus 102 degrees. Let's be plus 102 degrees plus beta plus 102 degrees is equal to 360. And the reason for this is angle at a point. So that's beta plus beta is 2 beta plus 102 plus 102 degrees is 204 degrees. This is equal to 360. Now we have 2 beta plus 204 degrees. So if we move 204 to the other side, we have 2 beta is equal to 360 minus 204. So from here, I clean up space. I add 2 beta, 100 as 156. So that's to get the value of beta here, I divide the sides at 2. This will be 2 beta divided by 2 is equal to 156 degrees divided by 2. We just cancel this, and beta 78 degree. That means beta here is 78 degree. If beta here is 78 degrees, this is, let me write it here, 78 degrees. If you look at this shape, this is a quadrilateral shape. So the shape we're looking at here is this shape here. If you notice, it looks like this. Okay, so this is a quadrilateral shape, and from that quadrilateral shape we can get the value of alpha. If we add all the angles in the quadrilateral, which is this angle plus this angle plus this angle plus this angle, we get equal to 360 degrees. Because angles in a quadrilateral, that's if you sum all the angles in a quadrilateral or a cycle quadrilateral, you get 360 degrees. So what that simply means for us here is that if we have alpha plus beta plus 90 plus 90, that simply is equal to 360 degrees. Now the reason for this is sum of angles in a quadrilateral. So I write quadrilateral here. So from here, what that simply tells us is that we have alpha plus, now beta here is 78 degrees, so this will be 78 plus 90 plus 90 is 180 degrees is equal to 360 degrees. Now if you add plus 78 plus 180 is 258 is equal to 360 degrees. If we make alpha subject to formula, we move 258 to the other side. So we have alpha is equal to 360 minus 258. So here you have alpha is equal to 360 minus 258 is equal to 102 degrees. So that means the angle of alpha here is equal to 102 degrees. Now remember, the arc that suspends the angle at the center is arc BD. So arc BD also, this arc here also suspends an angle to the circumference, and that angle happens to be theta. So that simply means that alpha is equal to 2 times theta. Now the reason for this is the angle at center is equal to 2 times angle at circumference. Now we know our alpha to be 102 degrees, so I'll simply say 102 is equal to 2 times theta. 2 times theta is simply 2 theta. So I can divide both sides by 2 from here. This cancels this. This would imply that theta is equal to 102 divided by 2. So 102 divided by 2 is simply 51 degrees. So the value of theta here is 51 degrees. So that's it on circle theorems. If you like the video, leave a thumbs up, share with your friends, and subscribe to the channel. It really helps the channel that you share, comment, and subscribe. And the video helped you, try to leave a comment in the description so that YouTube will send it to other people. Thank you for watching the video.